Mountains are some of the biggest things around, but something that big takes a lot of energy to create, and not all mountains are made the same way. But once a mountain forms, that's far from the end of the story. Sometimes it keeps growing. So here's how they go from a regular old piece of Earth to the tallest peak, at least for now, starting with the basics of plate tectonics.
At 8,848 meters above sea level, Mount Everest reaches farther into the sky than any other peak on our planet. It's often called the roof of the world, but it might also be pretty close to the ceiling, the upper limit of mountain height. See, a mountain can't just rise indefinitely. There are limits. Much of this has to do with how mountains form. Most major mountain ranges come about where two segments of Earth's crust are crashing slowly into each other. Though the Earth's crust is solid rock, it still changes shape under enough pressure. And when rock pushes up against rock, you end up with what's called crustal shortening as the plates squish together, and crustal thickening as the crust bunches and bulges like a carpet pushed against a wall. This can gradually push parts of a plate kilometers into the air, forming mountains through what geologists call uplift. Mount Everest and the surrounding Himalayas are a result of a particularly forceful collision between what is now India and the rest of Asia, which created a lot of uplift. But like with everything on this planet, gravity ultimately gets the final say. Mountains are really heavy, and that mass causes the underlying crust to bend and sag like a person sitting on a trampoline, which lowers the peak somewhat. And if those peaks grow tall enough, they can become so heavy that their weight overpowers the tectonic forces pushing them upward, and uplift stops. As the pieces of crust keep pushing together, the pressure leads to shortening and thickening under lower peaks instead, causing the slopes on either side of the central peaks to rise. So when the mountains can't grow upward anymore, they expand outward into plateaus. This has been observed in mountains all over the world, from the Rockies to the Andes to the Himalayas. And though we don't have an exact number for max height, we can assume Everest is pretty close to it, since it and other mountains in its range started growing outwards instead of up. But the mountain might be a bit shorter now than it used to be, and that's because there's another possible limiter on mountain size: ice. The idea is that once a peak reaches high enough into the atmosphere, glaciers begin to form, which then slowly carve at the summit. You see, mountains all around the world seem to top out at about 1,500 meters above the local snow line, an altitude which varies depending on the climate of the region. And this trend suggests that glacial erosion carves away mountains faster than they can grow their tallest peaks, a hypothesis known as the glacial buzzsaw. But there are some mountains that don't seem to suffer from the glacial buzzsaw: highly active volcanoes. It's not because their lava melts the ice or anything, but because they form somewhat differently from other mountains. Mauna Kea on the island of Hawaii measures more than 10,000 meters from its base at the seafloor to its peak, making it technically taller than Everest, though the majority of it is underwater. It's so big because it's a shield volcano that formed through successive eruptions depositing layer upon layer of lava. Like other mountains, Mauna Kea causes the crust beneath it to sag downward. It and its neighbor Mauna Loa depress the seafloor by as much as 6,000 meters. But that weight doesn't keep it from growing, since its growth doesn't depend on tectonic uplift. And it's thought that the speed of volcanic buildup can outpace glacial erosion. In fact, Mauna Kea probably would be taller, except it lost its fuel source. The mountain formed because a mantle plume beneath the crust produced magma, which powered the volcano. But now the plate has moved it away from the plume, slowing the pace of eruptions. There are bigger mountains in our solar system, though. On Mars, the crust doesn't move around like it does on Earth, and there's less gravity pulling things down, which is how Olympus Mons is able to reach a staggering 25,000 meters above the surrounding plains. Sadly, a mountain that large is probably not possible on Earth. Physics just aren't on our side.
So Earth's crust smashing into itself might not sound super sophisticated, but it definitely gets the job done. Unfortunately, that's kind of a brute force growth technique, and sometimes it has very devastating consequences, like leaving earthquakes in its wake. So here's more on how this side effect of growing mountains works.
It was late afternoon on March 27, 1964, when the ground in south-central Alaska began to shake as it never had before in North America, and never has since. For more than 4 minutes, centuries of accumulated compression were suddenly released. The magnitude 9.2 earthquake caused part of the Alaskan coast to lurch forward more than 20 meters. The resulting landslides and mudslides devastated towns and cities. In some areas, unstable land began to behave like water, causing buildings and roads and pipelines to sink into the ground, and dozens of tsunamis, the largest of which topped out at 67 meters high, caused catastrophic damage along the bays and inlets of the coast. More than 125 people died in the Good Friday earthquake, which was felt over an area of about 1.3 million square kilometers, and it released more energy than the combined power of every North American quake since. It's been 50 years since North America's largest recorded quake, and its legacy remains enormous because it was this natural disaster that ushered in the modern age of earthquake science. To understand what caused the Great Alaskan Earthquake, and really the majority of all earthquakes, we have to start with plate tectonics. Take a look at a map of earthquake activity today, and you'll find that most of the seismic events all over the world take place along the edge of oceanic and continental plates. There are 7 of them, all told, that together make up the Earth's lithosphere, the outermost shell of the planet where you find the crust and the upper mantle. These plates are constantly moving, and they interact with each other in lots of different ways. They can move apart from each other, creating a space known as a divergent plate boundary. When this happens, magma, the molten rock beneath the surface, usually seeps up to fill the crack and form new crust along the boundary. Plates can also push up against each other, creating what's called a convergent plate boundary. Tectonic plates move slowly, just a few centimeters a year, but over millions of years these collisions can create whole new mountain ranges as one plate is pushed up and the other sinks below the surface. Finally, tectonic plates can slide slowly alongside each other, creating what we call a transform boundary. You won't generally find any mountain ranges or lava along these boundaries, but you will find the makings for an active earthquake zone. All of these interactions seem pretty obvious to us today, but not so much just a half a century ago. The theory of plate tectonics had actually been proposed a full 50 years before the '64 quake by German meteorologist Alfred Wegener. But the idea that the Earth's surface floated around in pieces was ridiculed at the time, and Wegener's career was all but ruined. But in the decades that followed, new generations of geologists began discovering things like huge rifts on the ocean floor, which turned out to be the boundaries of Wegener's plates. Even so, by the early 1960s, some scientists saw new crust forming in the middle of the oceans, those divergent plate boundaries, as evidence that the planet was actually growing larger each year. That was the only way they could think of to explain where the other end of the plate had gone. That Alaska quake changed all that. At first, early in the quake's aftermath, some geologists tried to explain the disaster by theorizing that massive plates had just rotated past one another counterclockwise. But a handful of USGS scientists, led by George Plafker, knew that something else had happened, something we'd never studied before. Plafker and his team went to Alaska to study the land, and what they found was weird. In some areas, forests had been submerged under salt water, but in others, rocks with barnacles on them were standing on dry land. The land hadn't moved from side to side, it had moved up. We know it today as a megathrust earthquake, when one plate slowly slides beneath another in a process known as subduction. When the forces build up between these overlapping plates and one of them slips, the result is enough energy to move an entire coastline. Once Plafker and his team figured out what was going on, they realized that the Earth wasn't somehow growing in circumference like some geologists thought. Instead, the plates were recycling themselves in these subduction zones. As one plate slipped under another, it was forced down into the magma where it returned to a molten state. It turned out that the 2 plates involved in the Alaska quake, the Pacific and the North American plates, were the world's largest, making up about 1/3 of the world's surface. And of course, they're still colliding at a rate of about 5.8 centimeters per year, with the lighter North American plate being pushed upward. Today we know that all of the earthquakes with a recorded magnitude of 9.0 or higher, and there have been 6 of them since 1900, have been the result of one of these megathrust quakes. But thankfully, most earthquakes are not megathrusts. The majority occur along those transform boundaries where plates slowly slide past each other. It's this movement that will eventually cause Los Angeles, which is situated on the Pacific plate, to slide right past San Francisco, which sits on the North American plate. That will at least make commuting easier. Of course, this part of the Pacific plate moves about 50 millimeters to the northwest each year, so that'll take a while. And while earthquakes usually occur where tectonic plates meet, they can also happen far from their edges, because plate boundaries are just one type of fault, or fracture in the crust. Faults can form just about anywhere on a plate, as the result of a plate jostling around and bumping into other ones, or sometimes helped along by things like local volcanic activity. No matter what their origin, the constant buildup and release of energy geology in these faults are what cause earthquakes far from plates' boundaries. So-called normal faults, for example, form where the crust is being pulled apart and the ground above the fault zone drops. One of the largest normal faults in the US is the 240-kilometer-long Wasatch Fault, which extends through Idaho and Utah. As the North American plate moves to the southwest, it stretches, and this area of crust pulls it apart, forming the normal fault. Reverse faults, meanwhile, occur when the opposite occurs and pieces of crust are being compressed together, so the ground above the fault zone is being pushed up. These kind of faults are the Earth's great mountain builders. The Sierra Nevada, the Rocky Mountains, even the Himalaya are all the result of reverse fault dynamics, and it's also the type of fault that caused that megathrust in Alaska. Then we have strike-slip faults, where pieces of the Earth rub against each other sideways. California's San Andreas Fault is probably the most well-known of this kind in North America, while most of the earthquake activity in southwestern Europe is the work of Turkey's Anatolian faults. Like many other aspects of Earth science, we're still trying to understand all of the forces that cause earthquakes. And while the Alaskan quake ushered in a new era of knowledge in terms of how the Earth is pieced together, scientists are still trying to get a handle on questions like how different temperatures within the Earth affect seismic activity. And then there's the big question of whether and how we can predict them. It'd be nice if we could just monitor tectonic plates and send out warnings when a quake is imminent, but those plates are usually about 100 kilometers thick, and the process that occurs before an earthquake is subtle and pretty much impossible to observe. But maybe the most lasting legacy of the 1964 earthquake is all of the scientific institutions that now exist to study and monitor the activity of the Earth. The U.S. Geological Survey's Earthquake Hazards Program, the Tsunami Warning Center, and the Advanced National Seismic System, which monitors seismic activity around the clock, were all created in the wake of the Alaska quake to get a grasp on all the science that's going on right beneath our feet. And there's no shortage of data for them to study. There are more than 500,000 detectable earthquakes around the world each year, 100,000 of which can be felt by humans, 100 of which cause damage. The more we learn, the better scientists will become at predicting when and where earthquakes may strike.
So tectonic plates move in a ton of nuanced ways, and sometimes it results in earthquakes and mountains. But even with all of the variety in how the crust moves, that's not the only way mountains grow. Some mountains get their start with smashing crust, but then get taller through another mechanism, erosion. On SciShow, we've talked about all kinds of big, complicated questions like what happened at the start of the universe. But sometimes the questions that are hardest to answer are actually some of the simplest ones. Like, take mountains. Mountains have a profound impact on the rainfall patterns that shape our weather and climate. But how does rain affect mountain ranges? It seems like an easy question, but geologists have been debating the answer for more than a century, and some of their ideas aren't what you'd expect. Like, what if raindrops actually make mountains grow? If it's true, the implications could shape how we view the formation of the biggest features on our planet's surface. And after decades of searching, the final pieces of the puzzle are starting to emerge, thanks to some radiation from space. Oddly enough, the key to this idea is erosion, the process of wind, water, or ice wearing down a mountain by carrying away small pieces of soil and rock. And intuitively, knocking off bits of a mountain ought to make it smaller. And if erosion were the whole story, that would pretty much be the end of it. But that misses the complex effects of plate tectonics. Plate tectonics describes how Earth's crust is broken into moving chunks. But what matters here is what happens when those pieces come together. When two plates collide, their edges can get pushed up, creating a mountain range. And erosion can affect that process, both while it's happening and long after. It all comes down to erosion's ability to remove material from the mountains and thus weight. See, when mountains get lighter, they act differently. For instance, during the slow collision between plates, lighter plates will experience less friction as slabs of rock slide past each other on their journey upwards. And less friction means the tectonic forces have an easier time pushing the mountain upwards, making a taller mountain. Then there's another factor called isostatic equilibrium. That's the idea that the tectonic plates are essentially floating on the mantle, and their height is the balance point between gravity pulling down and buoyancy pushing up. Just like how an empty boat sits higher in the water than a fully loaded one. As mountains are eroded away and become lighter, they can float higher. So erosion can give an extra lift from below by accelerating the tectonic forces already in motion. Now, it's worth acknowledging what might seem like an obvious problem with this. Even if erosion makes a mountain lighter, it seems like wearing away the rock should also make the mountain shorter. And here, the key is that geologists think a lot of this erosion happens not on a mountain's peak, but but in river valleys lower down. These are areas of intense erosion, and by cutting into the side of a mountain, they can remove a lot of weight without removing a lot of height. So overall, it seems straightforward. Rain creates rivers, rivers erode mountains, the mountains become lighter and ultimately taller. Except here's the problem. All of this rests on that first idea, that rain drives erosion through rivers. But geologists have had an incredibly tough time proving that. Like, there are a lot of things that provide water for rivers, including rain, underground aquifers, and the seasonal melting of glaciers. So to claim that rain is the primary driver of the erosion that might grow mountains, someone needs to show that changes in rainfall actually correspond to changes in erosion. And isolating those details has proven so difficult to do that it took until 2020 to do this in a tectonically active mountain range. To do it, a team looked at how rain affects rivers cutting into the Earth's tallest mountains, the Himalayas. And to measure the rate of erosion, they relied on something kind of surprising: cosmic rays from space. Cosmic rays are highly energetic particles that come from the sun and beyond. And when they strike rock, they can sometimes interact with the minerals inside to produce a form of the element beryllium called beryllium-10. But this only happens for rocks near the surface, like during or after erosion. So when you look at a sample of eroded rock, the more beryllium-10 atoms you see in it, the longer it's been since it was eroded out of a rock. In the study, researchers used that information to figure out how fast erosion was happening in Himalayan river valleys in Bhutan and Nepal. Next, they built computer simulations of the rivers themselves, including their watersheds. Then they enter rainfall data into their river models to see if they could reproduce erosion rates that match what they observed using beryllium-10. And it worked! Erosion from their modeled rivers does in fact depend on how much rain falls in the area. And somehow, this is only one piece of the puzzle. The next step is to link these findings with a model of the tectonic forces to quantify how strongly this erosion affects the height of a mountain. But if scientists couldn't say with confidence that rain contributes strongly to the erosion effects of rivers, the rest would be kind of a moot point. So score 1 for finding the evidence needed to back up our hypotheses. It's not always the most glamorous part of science, but it's one of the most important for understanding our world. Even something as peaceful as rain can carve away at mountains and bring them to new heights. But that's after the mountain emerged in the first place. There are other mountains that didn't start out as the result of smashing crust at all. The Adirondacks likely had a slightly hotter origin story. Geology really loves its layers. Older stuff on the bottom, newer stuff on top. That is, until this planet of ours cooks, flips, and smushes those rocks every which way. Sometimes super ancient rock just sort of bubbles up out of the ground to build an entire brand new mountain range, such as New York's Adirondack Mountains. See, the rock on the high peaks of the Adirondacks is pretty old and rare. We're talking a billion years here. Yet the mountains themselves have only been around for 5 million years. To put that into perspective, multicellular life was only sort of a thing a billion years ago, whereas 5 million years ago, humans were probably splitting off from chimpanzees. Some of these particular rocks are also relatively uncommon, at least here on Earth. They're called anorthosite, an igneous rock that is one formed from magma that's pretty common in the higher elevations of the Adirondacks and is also found in samples from the moon. Anorthosite forms deep underground, where both the pressure and temperature are high, and it requires some pretty extreme conditions, like, say, 2 continental plates colliding, which is what happened to create the Grenville orogeny, a mountain building event roughly a billion years ago that created a huge range that was as high as the Himalayas and stretched from modern-day Canada all the way to Mexico. As part of that event, anorthosite got squeezed up from deep in the Earth's mantle, helping form these new mountains. But as time marched on, the Grenvilles eroded and the igneous material became buried in sediment. And around 400 to 500 million years ago, the mountain range was replaced by a shallow ocean. Over time, that seafloor accumulated new layers of sediment, burying the remnants of the Grenvilles under more and more material. But 5 million years ago, something happened in that corner of New York to lift up that old rock, forming a series of dome-shaped mountains. And geologists are only starting to understand how, because in this case, no new continental plates came together. It's more like upstate New York just decided to blow bubbles one afternoon. In 2018, a study published in the journal Geophysical Research Letters described 2 potential mechanisms for how the dome-shaped Adirondacks might have bubbled up from below. Around 100 kilometers below the surface of the Adirondacks is a layer of low-density light rock. Compared to the stuff around it, this rock is buoyant. Researchers think some of this material may have flowed upwards to fill cracks and expand, eventually accumulating enough to push everything above it up and
create a mountain. Another possibility is that heat may have played a role in expanding the rock and creating that same upward movement. In fact, the researchers think both mechanisms may have played a role. Regardless, the process is still happening today, with the Adirondacks rising at a rate of 2 to 3 millimeters per year, which adds up. That's 30 centimeters in a century. When the process started, the old igneous rock was still hidden under that newer sediment. But igneous rock is much harder than the sediments deposited at the bottom of the sea. So over time, the newer stuff eroded away, revealing the original billion-year-old rock, which is apparently how you upcycle a new mountain range out of an old one. The newer rock hasn't eroded away completely, and you can still find it around the edges of the mountains. But the peaks are that crazy old anorthosite. And that means the super old rock of the Grenvilles gets to ascend to brand new heights.
So heat expanded those rocks and helped them merge into mountains. But what if that never happened? What would Earth look like without mountains? In an alternate universe, Earth could have been totally flat and just covered in water. So here are some theories on how we avoided that fate and ended up with land as we know it.
Earth has land. You know that. Odds are pretty good that you're on some of it right now. But here's a weird thing to think about. It's possible that land didn't always exist, and technically speaking, it doesn't have to. I mean, if you were just to simply smooth out Earth's crust, the oceans contain enough water to cover the planet in a sea more than 2 kilometers deep. So, why does land exist? Why is it so varied with all those mountains and valleys and flat plains? And here's a fun one. Could anything ever get rid of land on Earth? To answer those questions, which God knows I want to do, you need to travel back more than 4 billion years. Billions of years ago, Earth started as a cloud of dust and grains left over from the sun's formation. Then, over time, those pieces slowly balled together into proto-Earth. That ball was made of all kinds of elements, and as it aged, the denser ones, like iron, sank toward the center of the ball to become the Earth's core, while the lighter ones stayed toward the outside. Eventually, the planet separated into the layers we know today: the inner and outer core, the gooey mantle, and the crust. These days, there are 2 main kinds of crust, continental and oceanic, and they are made of different ingredients. Oceanic crust tends to be mostly a type of rock called basalt and contains more heavy compounds, and continental crust, which generally makes up land, tends to be mostly granite and contains more relatively light compounds. But the composition of the early crust and how it changed in Earth's first billion years or so is pretty hard to pin down. Like a lot of Earth's early history, we just don't have much, or in some cases, any physical evidence. It's pretty much all been recycled and destroyed by now. So there are a lot of interpretations. But mostly, models seem to start with a crust that would more resemble oceanic crust today, with continental crust slowly growing over time. The exact date when the first continental crust appeared is one of the big questions in geoscience. Some models say it started growing almost immediately, others say it didn't really get going until about 3.6 billion years ago. But there's something potentially really interesting hidden in there, because depending on which of these models is right, early Earth might have been a water world. We think the oceans had to have existed by around 3.8 billion years ago. That's based on evidence like the ancient pillow lavas dated to around that time, which only form when lava flows into water. So if continental crust hadn't formed by then, there would have been a point in time at which the Earth was indeed an ocean world where land did not exist. So don't take land for granted. We could all be fish. As for why continental crust started forming, there are a couple ideas. One of the most well-studied relies on the movement of tectonic plates, the big slabs that make up Earth's crust, and it goes like this. At some point, the idea says, the crust started to form into these giant plates, possibly thanks to massive magma plumes from deep within the Earth. And as the plates started pushing against each other, some of them began sliding down towards the mantle in a process called subduction. And as that happened, the increased heat near and in the mantle began to heat the rock. But since rock isn't completely homogeneous, it's not like it all melted at once. Instead, different chemicals started to liquefy at different rates, and the rock separated in a process known as partial melting, with some of the areas being denser and others less dense. Over time, this process repeated, and we ended up with with new oceanic crust and the first continental crust material. That material was brought up through volcanic eruptions, which then built up into small volcanic islands above the ocean. The very first land, peeking its little head above the water. And as more volcanoes erupted and material got scraped off subducting plates, these islands would have grown over time into larger continents. Of course, like I said earlier, studying the beginning of Earth's history is hard, so not all scientists agree that subduction was necessary to build the first continents. Like in 2012, one group proposed something a little more like oozy. They got this idea while looking at rocks from the Isua Greenstone Belt in Greenland, which are more than 3.5 billion years old. They compared the amount of trace elements found in those rocks to amounts we'd expect to see if they formed by subduction, and they concluded that this ancient crust may not have needed to get all the way down into the mantle via subduction to melt and reform. Instead, it might have kinda oozed up as rocks melted higher up in the crust, so no subduction zone needed. No matter how this occurred, though, eventually Earth did get its first continent. Based on various pieces of evidence, some researchers have proposed that this continent, which they call Valbura, was made of rocks that are today found in southern Africa and Australia, while others favor a landmass made up of what would today be parts of India, Madagascar, and Australia. In any case, land happened, and as far as we can tell, Earth has had it ever since. Since the time of and Valbura, plate tectonics and other forces have kept continents above water and made them even craggier. These days, new continental crust is still being formed and destroyed at subduction zones, and plate collisions have also pushed up mountains, like in the Himalayas, making the Earth even less smooth. Meanwhile, erosion and other processes have also played a part, with wind and rain carving canyons, arches, and other amazing landscapes. So no matter how it got here, the land hasn't been unchanging and still. It's continually shaped, changed, and even sometimes been destroyed or completely hidden by forces of nature. And that makes you wonder, if all these forces are still at play, reshaping the landscape all the time, well, could those forces ever make land disappear? Well, the good news is continental crust is usually fairly stable. It's mostly the oceanic stuff that subducts and is recycled when plates collide. And today, the Earth has reached more or less equilibrium between the amount of crust made and the amount of crust lost. But some models have suggested that the amount of continental crust has actually decreased from some ancient peak. And a 2016 paper suggested that when India hit Asia, a substantial portion of the continental crust, like half of it, ended up being forced down into the mantle. Like, oh, bye-bye, land. Like, there you go. So it is possible to destroy continental crust on a large scale. But even then, land will probably never disappear entirely. Like I said, Earth seems to have reached a sort of equilibrium between crust made and crust lost. And we also have plate tectonics working to push parts of the ground higher and higher above sea level all the time. So even if some sort of catastrophic flooding happened, that wouldn't be the end of dry land. Even if plate tectonics stopped altogether, which for the record is really unlikely, since plate tectonics is powered by heat from the Earth's core, and that's not cooling down anytime soon, Earth still wouldn't become perfectly spherical. Scientists at Caltech noted that while erosion might wear the mountains down into hills, there would still be other processes. Things like meteorite impacts would still happen, which could create large dents in Earth's surface, little rings of land that would still stick out above the water. Volcanoes would still exist too, because although many are powered by magma from those all-important subduction zones, they can also exist far away from plate edges, like the hotspot under Hawaii. In those places, you don't need a subduction zone. Instead, magma plumes in the mantle are hot enough to melt their way up through the crust. In fact, while Earth is the only planet with active tectonic plates, volcanoes like this have created land on other worlds too. Like, even though it's dry now, Mars used to have a huge ocean, but it still had dry land, in part thanks to things like Olympus Mons, its gigantic, now extinct volcano. So even if Earth was a water world billions of years ago, the odds of that happening again are pretty slim. Which is great news, because while we probably haven't always had land as we know it, the fact that it does exist, well, has basically shaped everything about our species and also millions of others. And combined with the awesome forces of plate tectonics, erosion, and other geology processes, we've ended up with the vast and beautiful array of geography that we have today.
So it could have been magma plumes, volcanic islands, or oozy, melty rocks. Overall, heat seems to be a big player in mountain formation. But a lot of it comes down to pieces of Earth's crust hitting each other, and even pieces of rock from space hitting Earth. And if you're thinking that Earth can't be the only planet with space rock-made mountains, you'd be right. Here are some of the others.
When scientists try to understand the geology of the solar system, one of their most powerful tools is Earth. Our planet shares a lot with some of our neighbors, from our atmosphere up top all the way down to the spinning core. Sometimes, though, astronomers find things that don't look like anything here at home, places that couldn't even exist on Earth. And over the years, we've discovered some very unusual mountains. Take Rhea Silvia, a gigantic mountain on Vesta, the second biggest object in the asteroid belt. What makes Rhea Silvia so impressive isn't just how tall it is, but how tall it is relative to everything else. At about 22 kilometers high, it's nearly 3 times the height of Mount Everest, even though Vesta is only 500 kilometers across. That would be like a mountain 250 kilometers high here on Earth, tall enough to put you well into space. Rhea Silvia is more than just a mountain. It's also an impact crater, which might sound kind of strange since we don't normally think of holes making mountains. But the process of an asteroid slamming into the surface is so powerful that the ground briefly acts like a liquid and splashes back up, like a droplet of water falling into a pond. As everything cools down, that splash solidifies into a mountain called the central uplift. This process happens for basically every crater above a certain size, and we do have the remnants of some here on Earth. The impact that formed Rhea Silvia, though, must have been astonishingly powerful. Scientists think its remnants became some of the most commonly found types of meteorites. A central uplift isn't the only way an impact can form a mountain. Mercury is home to one of the solar system's most mysterious mountain ranges, and for decades, astronomers have thought it might be the result of an impact, but on the other side of the planet. This area doesn't have an official name, and it's a far cry from the peak of Rhea Silvia. The tops of these hills only rise from about 0.8 to 1.8 kilometers above the surface. What's more impressive is what's on the planet's far side, Cloer Planitia, an impact crater so large you could put 3 Vestas inside it with room to spare. This is the site of one of the solar system's most violent collisions, and its effects were global. When planetary scientists assembled the first surface maps of Mercury in the 1970s, they noticed something weird. These strange, low hills weren't just on the other side of the planet from Cloer Planitia. They were exactly opposite, at what's called the antipodal point. It's too perfect to be a coincidence. The impact must have created the mountain range through the planet. As impossible as that sounds, it probably happened because of Mercury's geometry. Mercury is a virtually perfect sphere, unlike Earth, whose fast rotation makes it fatter at the equator and shorter at the poles. When the Cloer impact occurred, it sent massive shockwaves through the planet. Because the path to the other side is the same distance in every direction, these waves converged at the antipode. Their combined strength deformed Mercury's surface and created the mountains. It's also possible that with less gravity and no atmosphere, material ejected from the crater traveled halfway around the planet to land on the far side. Between the shockwaves and all that flying debris, Mercury ended up with one of the solar system's most intriguing spots. Another is found at the other end of the solar system, way out on freezing Pluto. There, at the edge of its icy heart, lies a peak no taller than the Rocky Mountains, but much, much cooler. Like, figuratively and literally. It's named Wright Mons, after the brothers of airplane fame, and it's one of the best candidates for a cryovolcano. These volcanoes aren't too different from the ones you're familiar with, except for what makes up their lava. Pluto's crust is made of water ice, but in the seriously cold temperatures at the outer solar system, that ice has many of the same properties as rock here on Earth. So it only makes sense that a volcano on Pluto would have lava made of liquid water instead of liquid rock. Scientists aren't certain that Wright Mons or a nearby mountain that's also a candidate are cryovolcanoes. And it will probably be a long time before we get more observations of far-off Pluto. But cryovolcanoes do seem to be a thing in the solar system. There's potential evidence for them on Saturn's moon Titan and on the asteroid Ceres. It's not yet clear how they're possible in some of these places, and that's what makes them so interesting. Every mountain reveals the history of the area around it, even if you can't see that history directly. And in space, that's a tool for learning about some seriously weird geology that we might never have known existed otherwise.
And that's how to grow a mountain. They're definitely not one size fits all, so it might not be that surprising that they can form and grow in a variety of ways. Thank you for watching this episode, and thanks to our patrons for helping to make it possible. If you want to join our amazing community of patrons and help support SciShow, check out patreon.com/SciShow.